All right, let's talk about something we use every single second of every day, but maybe don't think about too much. Power. Specifically, how does electricity get from that outlet on your wall into that phone in your pocket? We're going to follow that journey, demystify those little power bricks, and figure out how our world actually gets powered up. I mean, just think about it. You've got that one drawer, right? The one that's just a complete rat's nest of chargers and power bricks for every device you've ever owned. So what's the deal with all of them? What are they actually doing? I mean, why can't you just, plug your laptop straight into the wall? Well, that's exactly what we're going to get into. Okay, so here's our game plan. First, we'll cover the big one, AC versus DC power. Then we'll check out the main tool for taming electricity in a lab. After that, we're going untethered to talk all about batteries and a little secret they're hiding. We'll look at the fine print, and finally, we'll see how you choose the right power source. All right, first things first, let's talk about the universal mismatch between the wall and your devices. This is literally the reason your charger collection exists in the first place.
So the juice coming out of your wall outlet, that's what we call AC, or alternating current. You can see it's this constantly reversing wave. It's super efficient for sending power over long distances, but for the tiny sensitive electronics in your phone or laptop, it's a total disaster. They need a smooth, stable, one-way street of electricity. That's DC, or direct current. So job number one for any charger is to act as a translator, to take that wild AC power and convert it into the calm, steady DC that our gadgets need to survive. So if you're an engineer or a student in a lab and you're building the next great gadget, how do you handle this? You can't just keep buying new chargers for every prototype. No, you use a special piece of gear designed to be the king of power conversion. And here it is, the benchtop DC power supply. Honestly, you can just think of it as your laptop charger on steroids. It's built to do one thing really, really well. Take that messy AC power from the wall and turn it into a super precise, totally controllable stream of DC power. This thing is the absolute workhorse of any electronics lab. But what makes it so special is the control it gives you. See all those knobs and terminals? This one's a triple output model, which means you can power 3 different parts of a circuit at the same time, each with its own unique voltage and current needs. You can dial in the exact numbers you want, and those little screens tell you precisely what's being delivered. It's all about precision.
Okay, so how much total oomph is this thing putting out? Well, it's pretty simple to figure out. You just need to calculate the power for each of those outputs and then add them all together. The magic formula is power equals voltage times current. So for our example here, we've got 36 watts from the first one, 27 from the second, and 5 from the third. You add all that up and you get a grand total of 68 watts of power being delivered. But here's the catch. To give your circuit those 68 watts, the power supply actually has to pull more than 68 watts from the wall. Why? Because nothing is perfectly efficient. There's always some energy lost in the conversion process, and that's what we call efficiency. It's just a measure of how much of that input power from the wall actually becomes useful output power for your device. So where does that lost energy go? It doesn't just vanish into thin air. It gets converted into heat. And yep, that's exactly why your laptop brick or your phone charger feels warm to the touch after it's been plugged in for a while. That warmth is literally the inefficiency of the power conversion process that you can feel. The more efficient the converter, the less heat it's going to generate. Okay, so that's how we power things when we're tethered to the wall. But let's be real, most of our lives are spent untethered. And for that, we need to dive into the world of batteries. At its core, a battery is just a little can of stored chemical energy. And when we talk about batteries, there's one spec that matters more than almost any other, the ampere-hour rating, or AH for short. This is the key number that tells you how much juice the battery can hold. Think of it as its endurance. And the best analogy for ampere hours? It's the size of a gas tank in a car. A bigger AH rating means a bigger tank. So a 100 AH battery, in a perfect world, could give you 1 amp of current for 100 hours straight. Or it could give you a massive 100 amps of current, but only for 1 hour. It's all about that trade-off between how much power you're drawing and how long it'll last. Let's put some real numbers on this. Say you're designing a small sensor with a 650 milliamp hour battery, and you absolutely need it to last for 2 full days, so 48 hours. A quick calculation tells you that your device can't draw more than about 13.5 milliamps on average. Or let's flip it. Maybe you have a device that's pretty power hungry. It pulls 2.5 amps, and you need it to run for half a day. Well, you'd better make sure you've got at least a 30 ampere hour battery to get the job done. Okay, but that all sounds a little too perfect, right? A little too clean. And it is. Because that number printed on the side of the battery, that AH reading, that's not the whole truth. There's a bit of fine print, and it explains so much about why our phone batteries die when we least expect them to.
And here it is, the big secret. The faster you drain a battery, the less total energy you get out of it. Yeah, you heard that right. That ampere-hour rating isn't set in stone. It actually goes down when you draw a lot of current. This is a real physical effect called derating, and it's baked into the chemistry of every battery.
This chart makes it crystal clear. Let's say we have that 100 ampere-hour battery. If you're just sipping power from it, say 5 amps, you'll get pretty close to that full 100 AH capacity. But if you start chugging power from it, like pulling 50 amps, its actual effective capacity might drop all the way down to 80 ampere hours. You've just lost a fifth of your battery's total energy, simply because you used it too fast. And that, right there, is the big aha moment. This is why your phone can sit at 100% for what feels like forever when you're just texting, but the second you fire up a heavy-duty game, the battery percentage just nosedives. Gaming is a high-current, high-power activity. It derates your battery in real time, making that last 30% of charge vanish way faster than you think it should. So, that gives us our two main contenders for DC power: the reliable, plugged-in lab supply, and the go-anywhere-but-finite battery. Time for a little head-to-head comparison. Looking at them side by side, the difference is pretty clear. The lab supply gets its juice from the wall, so for all practical purposes, its energy is unlimited. What you care about are its max voltage and current and how efficient it is. The battery, though, is all about that stored chemical energy. It's finite, so its most important number is that ampere-hour rating. It's pretty obvious, right? The supply is for building and testing stuff on your desk, and the battery is for anything that needs to be portable. All right, let's boil this all down to the three things you absolutely need to remember. 1. Power supplies and chargers are just translators, turning chaotic AC wall power into the clean DC our devices crave. 2. For batteries, it's all about ampere hours. That's the size of their fuel tank. And 3, and this is the big one for your daily life, that fuel tank actually shrinks when you step on the gas. A battery's real capacity goes down under heavy load. So, I'll leave you with this question. Now that you know all about derating, the next time you glance at your phone and see it's at, say, 30%, how are you going to think about that number? Especially if you're about to launch a power-hungry app. Because now you know the hidden truth. Not all battery percentages are created equal.